Hello, everyone. Today, I'll be talking about designing approximately optimal search on matching platforms. I'm Alex Wei, and this is joint work with Nicole Immorlica, Brendan Lucier, and Vahideh Manshadi. So the setting we'll be focusing on today is that of two-sided matching on online platforms. And so some examples are listed above. And as you can see, they've become ubiquitous as formers of social and economic connections in today's society. And many of these platforms have various elements in common, including agents having heterogeneous personal preferences over agents on the opposite side, the platform having imperfect data about these preferences, and the platform facilitating matching at a large scale through match recommendations. And so in this talk, what we will focus on is how should the platform design match recommendations in the face of uncertainty about agent preferences and strategic agents. And so the lens through which we'll study this question is through the lens of search. And so on many of these platforms, agents meet potential partners sequentially, and matches have to be mutually agreed upon that both people want to match. And so for example, you can see this on dating platforms where agents can meet people through looking at their profiles, and a match forms only if both people are interested. And so good match recommendations informed by the platform's data often drive the search process on many of these online matching platforms. And so another way to frame our question is, how should the platform design search, or how should the platform decide who gets to meet whom? And so as one might expect, good recommendations can greatly speed up search and make it much more efficient. But to make good recommendations, the platform should account for both its own uncertainty about agent preferences, including, for example, there are idiosyncratic preferences that the platform might just not know about. And the platform should also take into account user adaptation to changes in the search design. So to model this, this question, we present a model of search on matching platforms where the platform has distributional knowledge of agent preferences. And how this comes about is through agents come in different types, and types represent information about agents, either self-reported or inferred. And then the platform search policy sets how often agents of different types meet, and agents can strategically accept or reject potential partners whom they meet, and they do so to maximize their own expected utility. The platform then seeks a design that maximizes the overall welfare of the market. And so some challenges in this setting are that the platform must handle uncertainty about agent preferences that agents can strategically hold out for better matches. And so the latter actually can lead to congestion in the market, as well as cannibalization of different assortments offered by the platform. So how we're going to approach modeling this question is through a model where the platform has distributional knowledge of agent preferences, and this distributional knowledge comes in the form of knowledge about the preferences of types. And you should think of types as representing information that's either self-reported or inferred about agents. And the platform then introduces a search policy that determines how often agents of different types encounter each other. And at each encounter, agents can either accept or reject their potential partner, and they do so strategically to maximize their own expected utility. And the goal of the platform is to choose a design that maximizes the overall welfare of the market. And so challenges are that the platform has to handle uncertainty about agent preferences, and also that agents can strategically hold out and wait for better matches. And so this latter actually leads to congestion and also cannibalization of the platform's proposed matches. And from an algorithmic perspective, we give actually an efficient algorithm that finds an approximately optimal search design, despite the challenges listed on the previous slide. And actually, we get a stronger result, which is that our algorithm achieves 1/4 of the first best welfare, which is the welfare of the market outcome where incentives are not taken into account. We also show that approximation is algorithmically necessary, and that even finding a sufficiently good approximation is NP hard. And I'll get into more about this later, but our algorithm works by limiting meetings to submarkets determined by types. And these submarkets will have a simple structure. And so at a high level, takeaways that through careful search design, the platform can induce an equilibrium that has approximately optimal welfare. And this search design involves limiting agents' choice in the right way. So our work fits into several lines of related work in the literature. In economics, there has been a long history of studying search and matching markets, but these works assume random meeting of agents and don't consider the design problem of how should search be conducted. And there's also a recently blossoming literature on online matching platforms within the EC community. And so here are a few papers from this literature. Of course, there are many more. And so these are a couple of related works. And now I'll move on to presenting the model. And so in our model, we have a continuum model, which takes place in continuous time. And in this model, agents are going to have infinitesimally small mass. Each agent is going to have one of finitely many types, and types are going to be divided into two sides. So we're going to represent types by little data, the type space by big data, and then big data is going to be the disjoint union of types on side M and side W. And we'll use the run example of a dating market throughout. So you can think of M and W as corresponding to men and women. Then types enter with an arrival rate alpha, and then departure is endogenous. So agents either leave matched and so this is, so agents enter at an arrival rate alpha, and this is denoted in the blue arrow here. And then departure is denoted to the green and red arrows, where green is entering into a mutually agreed upon match, and red is leaving unmatched. Each type also has a population mass, eta, that is determined in equilibrium by inflows and outflows from arrivals and departures. And we're going to focus on stationary equilibrium. So we want inflows and outflows to balance. In terms of utilities, agents are going to have random symmetric cardinal utilities that are determined by their types. So each pair of agents is going to have a utility drawn from some continuous distribution determined by their types. And then utilities are going to be drawn independently from this distribution for each pair of agents, where this randomness represents idiosyncratic compatibility that's not available to the platform, or actually to the agents themselves either. And so what happens is that the platform knows the distributions, but the idiosyncratic compatibilities are only revealed to the agents when they meet. And so with the setup, the platform is going to determine the rates at which different pairs of types meet. And so here, type data agents are going to meet agents of type data prime. And this is going to take place according to a Poisson process with rate lambda determined by the data and data prime. And so when a pair of agents meets, what happens is that each learns their own utility for their shared utility for the match, and then each has the option to accept or reject. And they match and leave the market if and only if both accept, and they leave the market realizing their utility U. And so here on the right-hand side is our schematic again. And so here the the gray flows actually indicate the rates at which agents of different types meet. And so it's natural to actually expect that these meetings are subject to physical constraints. And so the first constraint is just simply a capacity constraint that agents experience at most one meeting per unit time in expectation. And so this is simply written as the sum of the agents' rates of meeting are at most one. And then second constraint is a flow constraint that equal masses of agents from any two types meet. And so this is just saying that the flows have to balance between any two types. And so now with the setup, we're ready to introduce the platform's design problem. And so this design problem, how this works is that the platform sets these rates lambda subject to the feasibility constraints. The rates induce a game among the agents. And so what we actually show, and this is a structural result that actually might be of general interest, is that under our assumptions, a unique Nash equilibrium always exists. And so we can actually talk about the welfare of a specific outcome. And then what the platform is going to do is it's going to optimize over the Nash equilibrium of these induced games that are sustainable in stationary equilibrium. And what the platform is going to optimize for is that the platform is going to try to maximize social welfare in the stationary equilibrium of these markets. And so they're going to look for the stationary equilibrium with highest welfare. And so we can actually write the platform's optimization problem as this rather ugly looking set of objective and constraints, encoding everything we've discussed so far, as well as highlighted in pink, this agent's best response condition, which says simply that agents play threshold strategies where they're best responding to other agents. And so this is a fixed point constraint. And actually, so tau theta appears on both sides and actually makes the problem quite challenging. And so, in fact, it's challenging in the sense that it's actually hard to approximate. So we formally proved that it's actually hard to approximate. It's NP hard to approximate to a factor better than 24 over 23. And in the paper, we also give examples showing that, sort of the intricacies that can arise when designing optimal search in terms of congestion and cannibalization. And so this is a hardness result. This is the bad news. But the good news is that we can actually derive an approximation algorithm for the setting. And this is what I'm going to present next. And so the algorithmic result that we obtain is that we show that the platform can efficiently find a for approximately optimal search design. And so what we show is that the welfare of our algorithmic construction actually for approximates the welfare of the first best outcome, which is a more optimistic benchmark. And here the first best is a setting that ignores individual agents' incentives and allows the platform to decide agents' decisions for them. And so how this algorithm is going to go is that we first construct an approximately optimal search. We construct first an optimal first best solution. And then we approximate this first best solution via star-shaped submarkets and lose only at most a factor of 4 in welfare. And so now I'll talk about each of these phases in more detail. So in the first phase of finding the first best, what we do is first we get rid of this challenging best response constraint from the optimization program. And so actually when we remove this constraint, somewhat surprisingly, the rest of this program simplifies. And so we can write it as an optimization program over pairs of the thresholds between pairs of types. And this reduces to a program that's like an assignment program. And so that's now written on the right-hand side, where the assignment weights rho are determined by the CDF's F. And so, and we'll use for the next phase, what we'll use from this assignment program is a structural property that the optimal solution is actually a bipartite graph over the types having the structure of a tree. And so it's a weighted bipartite graph. Or it's a weighted tree. It's both a weighted bipartite graph and a tree. And then, so the next step is we approximate via star-shaped submarkets. And what we do is we can approximate the tree with star graphs. And then we resolve for the first best in each of these star graphs, which correspond to the submarkets. And then finally, we adjust these submarkets to obtain stationary equilibria. And so each of these steps rebound the loss in welfare. And so we lose at most a factor of 4 in welfare overall. So that's the algorithm. And so now I'll briefly summarize and conclude. So in this work, what we did was we introduced this question of how should the platform design search on large-scale online matching markets. And so this platform has the challenge of both using its imperfect data about user preferences and dealing with strategic agents, and from while still making good recommendations. And what we show is that the platform can actually efficiently compute an approximately optimal search design for very general preference distributions. And so here's the sort of high-level takeaway again, which is that through careful search design, by limiting agent's choice, the platform can induce an equilibrium with approximately optimal welfare. And moreover, this search design, as we saw, lets us actually approximate the first best outcome. And so this is actually good search design means you can get close to efficiency. And also, we see that along the way, we also had a very simple solution structure, which has the added benefit of reducing the agent's strategic burden. Yeah, thank you for listening, and hope to see you at the poster session, or if you're interested, checking out the paper online.